So before I introduce the fundamental theorem of calculus, what I want to do is go back to the previous problem that we just did. We looked at the integral from 0 to 3 of 4x dx. What this represented is find the area beneath the curve between the graph of y equals 4x above the x-axis from x equals 0 to x equals 3. So find the area of that curve. We found it was a triangle, and when we did this, we found out that the area was 18. This was by using the geometric formula, area equals 1/2 base times height. We had a base of 3 and a height of 12. So that was what gave us our answer of 18. But now what I want us to do is I want us to consider what would have we done if we had the exact same problem, the integral of 4x dx, without the limits of integration. Well, if I didn't have the limits of integration, I would have used the power rule, and I would have said it was 4x squared over 2, which is 2x squared, right? So the antiderivative, and then I'd have the plus c, of course, right? So let me put the plus c in each one of those. When I integrate that, I would have gotten 2x squared plus c. Well, now what I'm going to do is I'm going to go ahead and I'm going to add back the integral limits from 0 to 3. And over here, I'm going to put a 0 to 3. And over here, I'm going to put a bar and a 0 and a 3. And this bar just tells me I still need to evaluate that from 0 to 3. So what am I going to do? I'm always going to plug in my upper limit first. I'm going to plug in my lower limit second. And I'm going to subtract the two values between them. Always subtract the two values. So this is called evaluating a definite integral. So let's just give this a try and see what we get. So it would have been 2 times 3 squared. I would still have the plus c, right? And then I'd have minus. And then I'd have 2 times 0 squared. That's my lower limit. And then I still have the plus c. Well, let's see what happens. First thing is 3 squared is 9 times 2 would be that 18, right? And then we'd have the plus c. I'm going to go ahead and distribute the negative. When I do this, I would have 0 squared is 0 times 2 is 0. So that would be minus 0. And then I'd have a minus c. So a couple of things that I want you to notice. Notice what happens with the plus c and the minus c. The plus c and the minus c are always going to cancel. Always going to cancel. The plus c and minus c are always going to cancel. So what could have we done? We could have gone back to our original problem where I had the integral of 4x dx, and I said it was 4x squared over 2 plus c. I never needed to put that plus c. I could have done it without that plus c. And then on the next line as well, I could have done it without that plus c, and I didn't need those plus c's right here because those c's are always going to cancel. So when I'm doing definite integration, when I have a lower limit and an upper limit, I know that I'm going to be evaluating this integral. I do not need to put plus c. If it's an indefinite integral, I always have to put plus c. Okay, so let's look at how we did this. If we finish this off, notice what we get as our answer is 18. Well, that's the same answer we got using the geometric formula. And the idea is now we see a direct application of indefinite integration. Why do we care about indefinite integrals? Well, we've been dealing with derivatives, which give us slopes, maximums, minimums, increasing, concavity, concave up, concave down. It gives us inflection points. So derivatives give us everything about the shape of a graph, everything about the shape of a graph, all that interesting information. When's it going up? When's it going down? Antiderivatives, doing derivative backwards, what's its primary application? Its primary application is now we are able to find the area of any shape. As long as we can find the function that models the shape of the graph, we can now find its area. How do we find our area? Well, you treat it just like it's an indefinite integral. Find out what the indefinite integral would be, but then remember that you're going to have to evaluate it. You're going to plug in the upper limit and then subtract off plugging in the lower limit. That is the fundamental theorem of calculus. So let's give a look at this right here. It says, the fundamental theorem of calculus. If f is a non-negative and continuous function on the closed interval, again, non-negative, we do have to be above the x-axis here. It does have to be continuous as well. All the functions we've been dealing with are continuous, so that's not an issue. On the closed interval a to b, then the integral from a to b of f of x dx equals f of b minus f of a, where f is any function such, capital F is any function such that the derivative of capital F is that lowercase f of x for all x in the interval. So in other words, what do you do first? So first, you're going to find the indefinite integral. Find the indefinite integral of the function. Like we've been doing in the last 3 sections, just find the antiderivative of the function, whether it be the power rule, whether you have to use u substitution, whether it's exponential or log. Just integrate like we've been doing for the last 3 sections. But now you're going to evaluate at the upper limit minus the lower limit. So you're going to evaluate it at the upper limit, and then you're going to subtract off evaluating the lower limit. And what I want to do is I want to put these in parentheses, because one of the biggest things here is people forget to distribute the negative. One of the biggest errors is forgetting to distribute the negative. So always put that when you evaluate it in the upper limit and the lower limit in parentheses, and you'll never make that error. So it says guidelines for using the fundamental theorem of calculus. The fundamental theorem of calculus describes a way of evaluating a definite integral, not a procedure for finding the antiderivatives. So what they're saying there is you need to use indefinite integration, all the different rules that we've learned for figuring it out. All the fundamental theorem of calculus says is to find that area beneath the curve from A to B, plug in B first and plug in A second into the antiderivative, but it doesn't tell you how to find that antiderivative. So let's look at an example that they work through right here. They're saying if we can think about what this question actually means, it's the integral from 1 to 3 of x cubed dx. So what they're looking at here is they're considering the graph of x cubed looks something like that, and they want to find the area beneath the x values of 1 to 3. So what's the area beneath the curve of f of x equals x cubed on the integral from 1 to 3? First of all, notice it is non-negative. It is positive in that interval, so we're good there. And it's saying all you have to do is, to find this, the fundamental theorem says, is integrate it as if it were not a definite integral. So what's the integral of x cubed? Well, using the power rule, that'd be x to the 4th over 4. And then notice they put that bar there, and they put the 1 on bottom, the 3 on top. And what that means is we still need to evaluate this. Okay, so you're doing the indefinite integral. I also want you to notice they didn't put the plus c. Again, they didn't put the plus c because we know the plus c's are going to cancel. So what do they do now? They plug in the upper limit, which was 3. They plug in the lower limit, which was 1. They plug this into their calculator, and they get the answer 20. So what's the area of that figure created underneath the curve of x cubed and the x-axis between those two on the interval from 1 to 3? The area of that would be 20. Whatever the units are, it would be those units squared. But again, in the x and y-axis, there are no units, so we don't even have to write units squared. So look at that. In part number 3, it says the constant integration, c, can be dropped because, and then it notices in the first one you have plus c, in the second one you have plus c, but the second you distribute that negative to that plus c, you would actually have minus c, and those two c's would actually cancel each other out. So there's no point in putting plus c when you're doing definite integration. Again, indefinite integrals, you always need plus c. Definite integrals, you never need plus c. So it says now with the fundamental theorem, the definition of a definite integral can be extended to include functions that are negative on all parts of a closed interval. So we can deal with negatives now on the interval a to b. It says specifically if f is any function. Now it doesn't need to be positive or not. And it is continuous on a closed interval a to b, then the definite integral of f of x from a to b can be defined as this. So now we're saying it doesn't need to be positive. It says where f is any antiderivative of f. Remember that definite integrals do not necessarily represent areas and can be negative, 0, or positive. So what the heck are they talking about there? Let's look at this. I want you to consider the function y equals negative 4x on the interval 0 to 3. So this is the exact example that we were looking at before, except now I've put a negative sign in front of it. So we would still have the same points. We'd have 0, 0, and then if I plugged in a 3, I'd have 3, negative 12 now. And when I plug this in, I still get a shape that's a triangle. And if I found the area of this shape, it would still be 1/2 base times height, which would still be 1/2 times the base of this is 3. The height of this is still 12. So this would still be an area of 18 units squared. But let's try it by doing the integral. If I said the integral from 0 to 3 of negative 4x dx, if I actually integrate this function, let's see what we would get. Well, if I do the antiderivative, it would be negative 4, and then I'd have x squared over 2. I would usually have my plus c, but it's a definite integral, so I don't need it. So that's from the integral from 0 to 3, the interval from 0 to 3. Negative 4 over 2, those are going to simplify into a 2, so I'm just going to clean it up. This is negative 2x squared on the interval from 0 to 3. Again, I cannot express how important it is to use parentheses here. I'm going to plug in the upper limit first. So this is negative 2 times 3 squared. Close that off in parentheses. Now I'm going to plug in the lower limit. Again, I don't need the plus c's because they're going to cancel. So this is a negative 2 times 0 squared. When I do this, 3 squared is 9 times negative 2 would be a negative 18. The second term, 0 squared is 0 times negative 2 is 0. And when I subtract off 0, I end up with negative 18. So if I do the fundamental theorem of calculus on this, I get negative 18. If I find the area, I get positive 18. So what this last part is saying is that the fundamental theorem of calculus, if we extend it to negatives, does not necessarily represent an area, as it can be negative, 0, or positive. So what it does tell us is, if you see a negative number here, in that sense, all that's telling you is that is below the curve instead of above the curve. Now it gets a little more complicated when we start considering functions that have both positive and negative areas. For instance, I'm just going to sketch a graph right here of sine of x on the interval from 0 to 2 pi. If you think about finding the interval of this, or the integral of this, you're going to have the red area, the first area, which is going to be positive. You're going to have the blue area, which is below the axis, which is the same size, which is negative. So if I actually integrated this curve from 0 to 2 pi, even though you don't know what sine x is necessarily, the red and the blue area are the exact same size. They would cancel each other out. And my fundamental theorem of calculus, if I use definite integration, would tell me that the area beneath the curve is 0. Well, clearly there's no area beneath the curve of 0 here. There's certainly a red area and the blue area. So there's different tactics when you start having functions that go above the axis and below the axis. In general, if you get a negative answer, that means the majority of the area is below the axis. If you get an area that's positive, it means it's above the axis. If you get an area of 0, it could mean, yeah, there is no area, or it could mean there's just as much positive as negative.